Hi guys, welcome back to part 4 of chemical reaction engineering quick revision notes. The last topic is thermomodulus. Thermomodulus is basically relation between catalytic activity and size of particle. It describes the relation between diffusion and reaction rate in porous catalyst. It is defined by the formula phi is equal to ml, where m is under root k by d. D is diffusivity. Like if there is a pore and on surface the concentration is CAS, concentration of surface, and within the size of the pore, like within length L, the concentration is CAL. So at any given height of the pore, any given distance length of the pore x, the CAL, concentration on length by concentration of surface, is equal to cos h m into L minus x by ml. There are two types of resistances, weak pore resistance and strong pore resistance. If our thermomodulus is less than 0.4, then it is weak pore resistance, and if it is greater than 4, then it is strong pore resistance. If there is what does weak pore resistance mean? It means that there is no resistance for the particle to move from the surface to the length L. So no resistance means that concentration on surface would be approximately equal to concentration at the length of the pore, which is CAL by CS would be approximately equal to 1. While in case of strong pore resistance, there would be high resistance, which means CAL by CAS would be approximately equal to 0. In case of weak pore resistance, our length, this length from surface to pore length, is low, which means shortest pore, and the reaction is slow, and diffusion rate is fast. While in strong pore resistance, the L length of the pore is high, largest pore is present, reaction is fast, and diffusion rate is low. In case of weak pore resistance, minus R, rate of reaction is equal to KCAL is equal to KCAS, and effectiveness factor is equal to 1. For strong pore resistance, effectiveness factor, what is effectiveness factor? It is basically rate of diffusion upon rate without diffusion. It is average of effectiveness calculated for our rate of reaction. Our effectiveness E average is tan H phi by phi. Phi is our thermomodulus. For phi greater than 4, which is for strong pore resistance, effectiveness average is 1 by phi, which is inverse of thermomodulus. For nth order, our thermomodulus is L, length of pore, under root n plus 1 into k Ca naught to the power n minus 1 upon 2 dE. dE is diffusivity, L characteristic length of the pore. For first order reaction, thermomodulus would be L under root k by dE. Effectiveness factor can also be written as rate observed upon KCA naught, which is equal to 1 by 5 for strong pore diffusion. Effectiveness factor is greater than 1 for non-isothermal and exothermic reactions. This is a point to remember. Reaction controlled by factor causing more resistance rate is inversely proportional to length. If change in length causes change in our rate of reaction, then strong pore diffusion is there, which means diffusion controls the reaction. One more point to remember, and this is very important point. If change in RPM do not affect rate of reaction, then external mass transfer do not affect the process. You have to remember this point. This is a very important point. So with this, we complete our revision notes, and the next video would be on questions.